Imagine trying to build a skyscraper, right?
Yeah.
But instead of using rigid steel beams, your scaffolding is made out of microscopic water-filled sponges.
Sounds incredibly unstable.
Right. And to make it even more bizarre, the tiny workers maintaining those sponges are completely isolated from any supply lines. They're essentially suffocating themselves just to keep the building standing.
Yeah, it sounds like an absolute architectural nightmare.
It really does. But that is exactly what your skeleton is doing, like right now.
It's true. It really challenges that comforting sort of static image we all have of a clean white X-ray.
Oh, absolutely.
We tend to think of our anatomy as permanent hardware, but the reality of our structural tissues is it's anything but static.
Well, welcome to today's deep dive. We are so thrilled to have you with us. We've been poring over a truly fascinating stack of medical and anatomical presentation notes today.
Really dense stuff, yeah.
Very dense. Breaking down the cellular histology of bone, cartilage, and some notoriously tricky anatomical landmarks. And our mission today is to sort of uncover the paradox of your body's hidden architecture.
Right, we're going to explore how tissues that seem, completely at odds with themselves mechanically manage to keep us moving.
Yeah.
We'll examine the biological trade-offs that make joint injuries so difficult to recover from and look at frankly, the brutal efficiency of how our bones actually form.
And to wrap it all up, we're going to untangle some anatomical tongue twisters.
Oh, the medical student's worst nightmare.
Exactly. Specifically the noids and the coids, which we will get into later. But to really understand the human skeleton, we can't actually start with bone, right?
You have to start earlier.
Right. We have to start with the unsung metabolic underdog that builds and pads the whole thing. We have to talk about cartilage.
Cartilage, yes.
Because when you look at the physical properties of cartilage, it's a total paradox. I mean, it is strong enough to withstand massive compressive force, yet it's flexible enough to bend without snapping.
Which is just a remarkable engineering feat.
Yeah.
How do you create a material that is both a shock absorber and a structural support at the same time?
It doesn't make sense.
To understand how it achieves that paradox, we have to look at the microscopic recipe. And cartilage is essentially made up of just two components.
Okay.
You have the cells themselves and the extracellular matrix, or the ECM, that they live inside.
Okay, let's unpack this, because looking at how these cells operate was a huge light bulb moment for me.
Yeah.
Yeah, because you start with mesenchymal cells, which are basically the body's blank slate stem cells.
Right.
And some of those get the signal to become chondroblasts, and they are the builders. They start secreting this massive matrix around themselves until they are completely trapped.
They build their own little cages.
Exactly. And once they are trapped, they mature into chondrocytes, and they live the rest of their lives isolated in these tiny, cave-like spaces called lacunae.
And from inside those little caves, they maintain that extracellular matrix.
Which is wild.
It is. Now, the matrix itself is where the biomechanical magic happens. If you break it down by weight, the extracellular matrix of cartilage is roughly 70% water.
70%.
Yeah, mostly water. The remaining 30% is organic material, primarily collagen fibers, and these massive complex molecules called proteoglycans and glycosaminoglycans.
Which we usually just call GAGs. Let's stick with GAGs.
As call, much easier to say.
And the GAGs are the key here. Things like chondroitin sulfate, calcarein sulfate.
Exactly.
Biochemically, these molecules are highly negatively charged. And if we remember basic physics.
Negative charges repel each other.
Right. So these molecules push away from one another, creating this stiff, bristly structure, almost like the bristles of a bottle brush.
That's a great visual.
But at the same time, those negative charges attract secretions, like sodium, which in turn draw in massive amounts of water. They are incredibly hydrophilic.
They act as an osmotic pump, essentially.
Right. So if you're picturing this, imagine those GAGs as microscopic, negatively charged sponges that literally suck in that 70% water content.
Yep.
That is the exact reason why they can resist the immense compressive forces of you running down the street or jumping off a step.
Because water doesn't compress easily.
Exactly. When you land, your body weight squeezes the water inside that sponge. The water resists being compressed, pushing back against the force.
What's fascinating here is how the biology regulates this down to the nanometer.
Oh, totally.
Because a proteoglycan is essentially a core protein with all those bristly gags attached to it.
Right.
But because these proteins come in so many different configurations, they don't just act as dumb sponges. They weave together to form pores of very specific sizes within that matrix.
Like a custom filter.
Exactly. They create a highly selective water-filled gel that perfectly dictates which exact molecules are allowed to move through the tissue.
It's just a genius design. But this brilliant design leads to a massive biological consequence.
It really does.
If this tissue is so perfectly engineered to be a durable, water-filled shock absorber, why does it have such a miserable time recovering from injury?
Oh, the classic problem.
Right. Anyone who has ever torn a meniscus or dealt with joint pain knows the cartilage just does not bounce back.
It does not. And the reason for that lack of recovery is one of the most defining features of the tissue. Cartilage is avascular.
Meaning there are absolutely no blood vessels inside it.
None. No blood vessels, no nerves, no lymphatic drainage in the extracellular matrix.
Wow.
Unlike bone, which is, packed with blood vessels and is incredibly metabolically active cartilage, is completely isolated.
So if you're one of those chondrocytes living in your tiny lacuna cave deep inside a knee joint, how do you even survive? You need oxygen, you need nutrients.
You are entirely dependent on diffusion. Most cartilage is surrounded by a dense layer of connective tissue called the perichondrium.
And that part does have blood flow.
The perichondrium does have blood vessels, yes, so nutrients have to leak out of those vessels on the periphery and then slowly seep or diffuse all the way through that dense, water-filled extracellular matrix to reach the cells in the center.
Okay, it's like trying to get a pizza delivered to a house, but there are no roads anywhere near it, so the delivery guy has to park a mile away and slowly wade waist-deep through a thick swamp to get to your door.
That is exactly the logistical nightmare these cells face.
A microscopic pizza delivery swamp.
Yes, and because of that swamp, the metabolic activity of cartilage is just incredibly low. The cells only get exactly what they need to survive, nothing more.
So they can't afford to expend energy repairing things.
Right, and this reliance on slow diffusion strictly limits how thick cartilage can physically grow. If a piece of cartilage gets too thick, the nutrients simply can't diffuse fast enough to reach the deep center.
And those inner cells would just starve and die.
Exactly.
Which explains why injuries are so devastating. If you have a severe tear in your adult cartilage, it can't quickly ramp up production to fix it. It doesn't have the supply lines.
It's structurally bottlenecked.
Yeah. The notes we're looking at point out that aside from young children who have a slight capacity for regeneration, adult cartilage basically just gives up.
It defaults to scar tissue.
Right. The surrounding perichondrium panics, sends in fibroblasts, and produces a dense connective tissue scar. You lose your beautifully engineered shock absorber and get a rigid scar instead.
Which doesn't help with joint movement.
Not at all. But I have to ask, from an evolutionary standpoint, this seems like a massive design flaw. We rely on our joints to hunt, gather, and survive. Why leave our primary shock absorbers metabolically starved?
It does feel like a flaw, doesn't it? But until you look at the mechanics of human movement, it doesn't make sense. If we connect this to the bigger picture, the avascular nature of cartilage is actually a mandatory structural trade-off. Think about the physical environment inside your knee or your hip. Those joints endure immense, repetitive, crushing pressure.
Sure, every time we take a step.
Exactly. So if that gel-like matrix was packed with a delicate network of blood vessels, what would happen every single time you took a heavy step?
Oh, you'd be crushing the blood vessels flat. They would just burst.
Precisely. You'd be dealing with catastrophic internal bleeding and swelling inside your joints constantly.
Oh, wow.
The very avascular gel-like structure that allows cartilage to compress and absorb shock is exactly what prevents it from having an internal blood supply. It cannot have roads because the roads would be instantly destroyed by the traffic.
Okay, so we sacrifice the ability to heal quickly just to ensure our joints don't hemorrhage every time we go for a jog.
It's a brutal compromise.
Yeah, it's a brutal compromise, but it makes perfect sense. So the body is stuck with its limitation. But what I love about anatomy is how the body gets creative with its constraints.
It really does.
It basically tweaks the recipe of this matrix to serve different mechanical needs. We see 3 distinct variations or flavors of cartilage across the body.
And they all share that base ingredient of type 2 collagen, which forms a fine, subtle mesh. But the additives define their function. The first and most ubiquitous is hyaline cartilage.
Right. Hyaline is your standard everyday cartilage. It's glassy and smooth. It uses that baseline type 2 collagen, and you find it capping the ends of your bones and your joints, giving them a friction-free surface.
It's the classic joint padding.
Yeah. It also keeps your major airways, like the trachea and bronchi, propped open so they don't collapse when you inhale. And it makes up the septum of your nose.
Then you move to the second variation, which is elastic cartilage.
Okay.
As the name suggests, the body takes that hyaline recipe and weaves in a dense network of elastic fibers.
And there's a fascinating detail about how we even know this tissue is different.
The staining process?
Yes. If you just look at hyaline and elastic cartilage under a standard microscope, they look almost identical. The cells in the matrix just blend together. Scientists actually have to use a specific chemical dye called a Weigert stain.
Right, the Weigert stain.
When they apply it, the elastic fibers suddenly stain pitch black, revealing this dense, flexible web hidden inside the tissue.
It really highlights how reliant structural biology is on chemical tricks just to map the body.
Completely.
And those black staining elastic fibers give the tissue pliability. This is the cartilage forming the external flap of your ear.
So that's why we can bend our ears around.
Exactly. It's also in your epiglottis, the flap that folds over your windpipe when you swallow.
Oh, that makes sense.
It has to bend completely out of shape and immediately snap back to its original form thousands of times a day without fatiguing.
Which brings us to the third type, the heavy-duty stuff, fibrocartilage.
Fibrocartilage is the ultimate biological shock absorber. You find it in areas subjected to massive pulling forces and extreme compression places like the intervertebral discs in your spine or the menisci in your knees.
So the high-stress zones.
Exactly.
Yeah.
And to handle that, the body significantly upgrades the recipe. It is the only type of cartilage that contains dense bundles of type I collagen fibers on top of the standard type 2.
And type I is fundamentally different, right? It's the same thick collagen you find in tendons.
Yes, very thick, very strong.
Instead of a fine mesh, it forms these thick parallel bundles. I imagine it like the thick steel cables on a suspension bridge, giving the tissue immense tensile strength so it doesn't just squish under pressure, but actually resists being pulled apart.
That's a perfect analogy. The parallel alignment is key to handling directional stress. And a prime example of fibrocartilage doing heavy lifting is in the pubic symphysis.
Right, the joint connecting the two massive halves of your pelvis.
Exactly. Under normal circumstances, that fibrocartilage holds the pelvis firmly together. But during labor, the body orchestrates an incredible biomechanical shift. It releases a hormone brilliantly named relaxin.
Very on the nose.
Yeah.
And relaxin specifically targets that fibrocartilage.
Yes. It chemically alters the matrix, increasing its water content and loosening those heavy-duty fibers.
Wow.
It forces the pubic symphysis to become temporarily pliable, allowing the rigid ring of the pelvis to literally expand so the baby can safely pass through the birth canal.
It temporarily melts the suspension bridge cables.
In a way, yes. But it highlights another physiological trade-off.
Yeah.
By compromising the structural integrity of that heavy-duty fibrocartilage to facilitate birth, the joint can become unstable. It's why some individuals experience significant pelvic and joint pain long after delivery.
Because that highly specialized shock absorber takes a massive, sometimes permanent mechanical hit.
Exactly.
And here's where it gets really interesting. Fibrocartilage doesn't even have a perichondrium.
It does not.
That outer membrane that feeds normal cartilage with nutrients. Fibrocartilage doesn't have it. It's under so much grinding mechanical stress that an outer membrane would just be shredded.
It wouldn't survive a day.
Right. And articular cartilage, the smooth hyaline cartilage inside your knee and elbow joints, is the exact same way. It lacks a perichondrium because it acts as a friction surface. So they just have to absorb whatever sparse nutrients they can from the synovial fluid floating around the joint. They are truly living life on the edge.
They are entirely optimized for mechanics over metabolism.
So if cartilage is stuck in this avascular, slow-growing state, limited by how far nutrients can diffuse through a swamp, how on earth does a developing embryo use it to rapidly build an entire rigid skeleton?
That is the ultimate biological pivot. Because cartilage isn't just a shock absorber, it is the physical blueprint for the vast majority of your bones.
The blueprint.
Yes. Around the 6th week of embryonic development, the body begins a process called endochondral ossification.
Break that word down for us.
Sure. Endo, meaning inside, chondral, meaning cartilage. So bone forming from the inside of cartilage.
And walking through the steps of how this happens, I mean, it is a masterclass. and brutal sacrificial efficiency.
It really is a hostile takeover.
It starts with the body building a tiny, perfectly shaped model of a long bone, like your femur made entirely out of hyaline cartilage.
It's just a temporary scaffold.
Right.
But to turn that soft scaffold into hard bone, the cartilage cells have to orchestrate their own destruction. The chondrocytes right in the center of the shaft begin to dramatically enlarge, a process called hypertrophy.
They swell up.
Yes, and as they swell, they alter the surrounding matrix, causing it to calcify and harden.
But remember, cartilage relies on diffusion. Nutrients can't diffuse through a hardened, calcified wall.
Exactly.
So by calcifying their own matrix, these giant chondrocytes completely cut off their own food supply. They starve. They literally build a hardened tomb for themselves and die, leaving behind empty, calcified cavities.
And that cell death is the exact biochemical trigger needed for the next phase.
The invasion.
The invasion. Once the cartilage matrix breaks down and the cells die off, blood vessels finally invade the center of the structure. They break through the perimeter and flood those empty cavities. And riding along with those blood vessels are the osteoblasts, the bone-building cells.
So cartilage cells sacrifice themselves to clear out the swamp and pave the way for a superhighway of blood vessels.
Exactly. The osteoblasts use that calcified cartilage debris as a framework. They establish a primary ossification center and start laying down true, vascularized, metabolically active bone tissue.
Wow.
Eventually, the same process occurs at the ends of the bone, creating secondary ossification centers. But crucially, to allow a child to continue growing taller, the body doesn't replace all the cartilage at once.
Right. It leaves a narrow band of hyaline cartilage between the shaft and the ends, the epiphyseal plate or the growth plate.
The growth plate.
And this plate is in a constant state of dynamic equilibrium. On one side, it is furiously multiplying, churning out fresh cartilage. On the other side, that new cartilage is constantly calcifying, dying, and being replaced by bone.
It's an endless chase.
Exactly. The bone actually lengthens by chasing this retreating line of cartilage until you reach adulthood and the plate finally seals shut. So what does this all mean for you? It's just microscopic violent cells building a house just to die inside it so blood vessels and bone cells can take over and upgrade the structure.
It is an incredibly elaborate sequence of construction, destruction, and replacement. But, this highly coordinated system isn't used for everything. No. If we look at the skull, the body completely abandons the cartilage model. It uses a second method called intramembranous ossification.
Intramembranous. So, forming inside a membrane. There is no hyaline cartilage blueprint at all then.
None at all.
Instead, the flat bones of your skull and your jaw, the mandible, form directly from a fibrous connective tissue membrane. Osteoblasts just cluster within this membrane and start secreting bone outward. Why? The completely different set of blueprints.
This raises an important question, right? And it comes down to the massive functional constraints of human birth.
Okay.
If your skull formed through endochondral ossification, the bones would be preceded by thick, rigid blocks of calcifying cartilage very early on. You would have a solid, inflexible box surrounding the developing brain.
Which would be a problem during delivery.
A huge problem. Intramembranous ossification, however, allows those flat bones to radiate outward within the flexible membrane, but it purposefully leaves large, unossified gaps between the plates.
Oh, the fontanelles, the soft spots on a baby's head.
Yes, those soft spots are a biological imperative. During childbirth, those fibrous gaps allow the cranial plates to literally deform and overlap one another, a process called molding.
So the fetal head can safely pass through the narrow birth canal without fracturing.
Exactly. It's only months and years after birth that those membrane gaps finally fill in and suture together into a solid protective vault.
It is stunning to think about. You have cells in your legs building a cartilage house just to die inside it so blood vessels can upgrade the structure to support your weight. Meanwhile, your skull took a completely different membrane-based construction route just to ensure you could survive the physical trauma of being born.
The evolutionary logic is just breathtaking.
It really is.
It perfectly illustrates that anatomy is never random. Every tissue type, every ossification pattern exists to solve a very specific mechanical problem.
Which provides the perfect transition to the final challenge of our deep dive. Because we've talked about how these bones form and the structural logic behind them. But when you actually look at the finished skeleton, it is covered in ridges, bumps, and hooks.
So many hooks.
And medical professionals have to name and memorize all of them.
The nomenclature of anatomy. It is dense, it is largely derived from ancient Greek and Latin, and it is notoriously unforgiving to learn.
To put it mildly, the anatomical notes we're looking at highlight three specific bony projections that sound virtually identical, but are located in completely different parts of the body. We're talking about the noids and the coids.
Yes.
The carnoid, the coracoid, and the conoid.
It's the classic triad of confusion for anyone studying the skeletal system.
I mean, they sound less like human body parts and more like a vintage sci-fi alien species.
Really do.
But functionally, these aren't just random bumps. They are massive anchor points for muscles and ligaments. So let's actually map these out, because the naming logic is fascinating once you break it down. Let's start with the coronoid process, with an N.
Okay, so the term coronoid generally stems from the Greek word koronae, which can mean a crown, but in anatomy it often refers to something shaped like a crow's beak or a hook.
A hook. Okay.
And there are two distinct coronoid processes in the body.
Right. One is on the mandible, your jawbone. It's an upward-pointing triangular hook of bone. And its function is critical. It serves as the attachment point for the temporalis muscle.
The chewing muscle.
Yeah, that's the powerful muscle on the side of your head that allows you to bite down and close your jaw.
The second coronoid process is located on the ulna, which is the bone on the pinky side of your forearm. It's a prominent lip of bone situated right at the elbow joint.
So when you bend your arm...
Right, when you flex your elbow, that coronoid process hooks directly into a matching depression on your upper arm bone, the humerus.
Locking the joint into place.
Exactly, preventing it from hyperextending.
Okay, so coronoid, the hook, is the jaw and the elbow. Both are hinged-like joints that need strong locking and pulling mechanisms. Now, moving to the coracoid process, with a C.
The coracoid process is a thick, curved projection of bone extending from the scapula, your shoulder blade. It points forward, coming right over the top of the shoulder joint.
Oh.
The name also traces back to a raven or crow's beak, which honestly doesn't help with the confusion at all.
No, not at all.
But functionally, it is vital. It acts as the primary anchor point for several key structures, most notably the short head of the biceps muscle. Without the coracoid, the mechanics of lifting your arm forward would just collapse.
Wow. And finally, the conoid tubercle.
The conoid tubercle is a small cone-shaped bump. It's located on the underside of the clavicle, the collarbone. It anchors the conoid ligament, which ties the collarbone directly to the scapula, stabilizing the entire shoulder girdle.
So we have coronoid at the jaw and elbow, coracoid at the shoulder, conoid at the collarbone. The presentation notes provide a brilliant, simple mnemonic for keeping the main three straight.
Oh, I love this one.
If you're listening, try mapping this on yourself right now. The phrase is, coracoid lies between the two noids.
It's an incredibly elegant piece of cognitive scaffolding.
It really is. Touch your jaw. That's the coronoid hook. Now trace a line straight down to the front of your shoulder. That's the coracoid beak. Now trace the line down your arm to your elbow. That's the other coronoid locking mechanism. The coracoid lies between the two noids. Jaw, shoulder, elbow. Coronoid, coracoid, coronoid.
And, while mnemonics like that might seem like simple student crutches, they are absolutely essential in practice.
That's so.
When a surgeon is operating or a radiologist is interpreting an acute trauma on an X-ray, they are processing massive amounts of overlapping data.
Right, they can't be guessing.
They cannot afford a split-second cognitive lapse where the Latin roots blur together. Tools like this synthesize the complexity and allow professionals to navigate the anatomy safely and instinctively.
It's the hidden architecture of the medical brain at work. Well, that brings our deep dive into these anatomical blueprints to a close. Let's quickly retrace the path we took today.
Sounds good.
You learned that your skeleton relies on microscopic, negatively charged sponges that repel each other to pull in water and absorb the shock of your footsteps.
A very precarious system.
Very. You learned that you sacrifice the ability to quickly heal your joints just to ensure they don't burst with blood under pressure. You discovered the brutal biological calculus of your arm bones calcifying and destroying their own cartilage models to grow, while your skull formed in a flexible membrane just to ensure you could be safely born.
It's amazing when you put it all together like that.
And finally, you can now confidently map the noids and coids anchoring your upper body.
It is a profound amount of physiological engineering to think about. But before we wrap up, I want to leave you with one final thought to explore on your own.
Okay.
Something that challenges everything we established about the tragedy of cartilage.
Ooh, I love when we can flip the script. What are we looking at?
We spent a lot of time discussing how cartilage heals terribly because it is fundamentally avascular.
Right, the pizza delivery swamp.
Exactly. It relies on a slow swamp of diffusion, preventing it from ever ramping up a regenerative response. But what if we didn't have to accept that constraint permanently?
What do you mean?
What if, in the near future, bioengineering could temporarily rewrite the rules of histology? Imagine a treatment where we could induce blood vessels to temporarily grow into a severely torn knee meniscus.
Wait, really?
Yeah, we flood the area with a rich, hyperactive blood supply, turning that swamp into a metabolic superhighway just long enough for the cartilage to fully reconstruct itself.
Okay, but then wouldn't walking on it just crush the vessels again?
That's the trick. Once the tissue is healed, we trigger those newly formed blood vessels to completely recede and die off, returning the joint to its native vascular shock-absorbing state.
Wow, you temporarily turn the joint into a construction zone, drop off the materials, and then bulldoze the roads on the way out so the heavy traffic doesn't ruin the finished product.
Precisely. It would effectively cure osteoarthritis. It would mean the end of permanent joint scars.
That would revolutionize orthopedics.
It really would. It reminds us that while evolutionary constraints are deeply ingrained, the boundaries of medical science are constantly pushing against them.
That is an incredibly exciting thought to end on. So the next time you look at an X-ray or see the steel beams of a skyscraper, remember that the solid white lines are only half the story. The true hidden architecture holding you together is the invisible, water-filled, perfectly engineered gel sitting quietly in the dark. Thank you so much for joining us on this deep dive. Keep questioning the amazing, complex machinery of your own bodies, and we'll catch you next time.